have learned a lot of different techniques for integration. You've learned the basic properties, how to do a U substitution, and some of the other log forms and that sort of thing. What we're going to look at in this lesson is integration by parts. Now, integration by parts is a result of the product rule for finding derivatives. Recall that if you have a product of two functions and you're finding the derivative, that it was rather complicated, wasn't it? You couldn't just take the derivative of each function separately. So you might imagine that if you have a derivative that resulted from a product rule, that perhaps finding the antiderivative might be a little bit more difficult. Let's look at the product rule and see how we can develop this formula called integration by parts. The derivative of a product, the derivative with respect to x of u times v, and you're just assuming these are both functions of x here, equals u times the derivative of v with respect to x plus v times the derivative of u with respect to x. Now I'm going to take this formula and first of all just rewrite it a little bit. I'm going to solve for this term right here. So I'm going to write it first. U times dv dx would equal the derivative with respect to x of u times v minus v times the derivative of u with respect to x. I just subtracted this term from this and then just wrote it in a different order here. In this form, I'm going to find the antiderivative with respect to x of each part of this. Okay? Notice here these dx's will cancel. So I have the integral of u times dv. Now on this part, if you have the derivative with respect to x of this, and you find the antiderivative with respect to x, then you have what you started with there. In other words, you took the derivative of this with respect to x, then you found the antiderivative with respect to x, so you're back where you started. So you have u times v. Here these dx's cancel. You have minus integral v times du. I just wanted to show you this, not that you have to remember how this is developed, but I wanted to show you this so that when you see this integration by parts formula, you know where it came from. It says if u and v are functions of x and have continuous derivatives, then the integral of u times the differential of v, u times dv, equals u times v minus the integral of v times the differential of u, v times du. You need to commit this formula to memory. I'm going to suggest that as you do your homework problems on this integration by parts, that you write this down at least for the first several problems, because if you'll write it down and think about it as you're writing it down, you'll have it memorized after you do just a few problems. Now we're going to see how we can use this formula to find antiderivatives of functions that we would not be able to do by other techniques. The first example that I'm going to do is to find the antiderivative, or the integral, of x times sine x dx. Now, a u substitution will not help us with this example. So what we're going to do is set it up in that parts format. Now, I want to comment a little bit about the initial part. We're starting right here. So what we have to do is to take our integral, identify part of it as u and part of it as dv. Okay? Now, I will be giving you some guidelines after we do this example, but what I'm going to do right here is I'm going to choose u to be the x that I see right here, and I'm going to choose dv to be the sine x dx. Now, a couple of things. The dx will always go with the dv, all right, because we're talking about differentials here. You also have to be sure that you have accounted for everything that's in this integrand up here. I have the x accounted for here. I have the sine x and the dx accounted for here. I have left nothing out. Part of it either went for u or for dv. Okay? Now, once I've taken my initial integral and identified part of it as u and part of it as dv, the next step is to look at what we've written right here and use this, first of all, to find du. So if u equals x, du would equal 1 times dx, wouldn't it? The second part is to take this and say the antiderivative of dv will equal the antiderivative of sine x dx. Now I'm going to put this down the first couple of steps here. Usually I don't write this step, I just think it. But the antiderivative of 1 with respect to v is a v. And the antiderivative of sine x dx would be negative cosine x. Okay? Now, since we have found u dv, we found du, and we integrated to find v, now we're going to use this formula here. Let me write it for you so we can refer to it up here. The integral of u times dv equals u times v minus the integral of v times du. Now, we have right here u and dv. Okay? So this integral, this u dv integral, is equal to, first of all, u times v. We'll look down here. Here's u and here's v. If we multiply u times v, we'll have x times negative cosine x, which we can write this way, negative x cosine x. We've multiplied u times v. Then notice we have minus the integral. Here we have v times du. Here's v and here's du. So multiplying those, we would have negative cosine x times dx. Okay? U times v is here, minus integral v times du. Now, let's look at what we have written, and I'm going to bring it down here. I have minus x times the cosine of x. This is a negative 1 times this cosine, so we can pull it out here, and negative 1 times negative 1 will make a plus 1, antiderivative or integral of cosine x dx. We know how to do this one, don't we? So we're going to continue to come down. Minus x cosine x, and the antiderivative of cosine x is sine x. And then recall, this is an indefinite integral, so we're going to put on a plus c. Now, I want you to look at this answer. Recall that we can check to make sure this answer is correct by taking its derivative and seeing if we have the integrand right here. I'm going to check this first one just so you can see that this process does work. After the first one, I will not check these. Let's take the derivative of this. Notice right here I have a product of two functions, so I have to use the product rule here. The first function is negative x times the derivative of the second function, sine x, plus the second function is cosine x times the derivative of the first function is negative 1. So I've used the product rule here. Now I'm here. Plus the derivative of sine x is cosine x. The derivative of the constant is 0. I'm going to put that down for emphasis. Now let's simplify. I have negative x sine x minus cosine x plus cosine x. Oh, you know what? I made a mistake here. The derivative of cosine is negative sine. I didn't get my negative on that. So this will be a plus x sine x. I apologize. I was thinking antiderivatives, I think, instead of derivatives. The derivative of cosine is negative sine. So let me make that correction. Now, notice here, these drop out. I'm left with x sine x, which is exactly what I had in the integrand here. So we do have the correct answer here, and we have found it by using this parts format. Now, I just simply chose for you the u and the dv and showed you that this worked in this example. But of course, when you do problems, you have to make those decisions. So I have some guidelines. Let dv be the most complicated part of the integrand that has a basic integration formula. Simply put, you want dv to be something that you can find its antiderivative. Now, the second part of our guideline is to let u be the portion of the integrand whose derivative will be a simpler function. Notice in this example that I just did, by choosing u to be x, the derivative became a 1, which is simpler than just the x. If I had chosen u to be sine x, the derivative of that would have been cosine x. That's basically equal difficulty. It did not get any easier. But sine x, even though it's rather complicated, is a function that I can find its antiderivative of. Okay? So those are our guidelines. We want u, so that when we find that du, hopefully it gets easier. We want dv to be complicated if it needs to be. That's all right, as long as we can find its antiderivative. So let's see how to apply those guidelines. I want to find the integral of x squared times cosine x dx. Now this is going to be similar to the example we did a moment ago, but just a little bit more complicated. Again, my first step is to choose part of this integrand to be u and part of the integrand to be dv. Recall, I want u to be something like the x squared here because the derivative is going to get easier. I want the dv to be as complicated as it can be and yet still be able to do this, find an antiderivative, which I can do with this cosine function. Notice if I had put x squared here, the antiderivative would have gone up to x cubed and it would have gotten more difficult. Whereas the antiderivative of a cosine function is not really going to be any more difficult. Of course, it's not less difficult, but it's not any more. Okay, with these choices, u equals x squared. So du is 2x times dx. See, that got easier. The antiderivative of dv is v, and the antiderivative of cosine x is sine x. All right, our parts formula, remember the integral of u times dv is u times v minus the integral of v times du. That's what we're going on. So I have u and v. If I multiply those, I have x squared times the sine of x, u times v, minus integral v times du. Okay, so I have 2x times sine x times dx. Just remember, we usually write that dx at the end. So multiplying v sine x times the 2x dx. Now, if you want to move this 2 out front, since it's a constant, you can do that. I would just as soon leave it there. But notice that I'm going to have to do parts a second time to be able to find the antiderivative here. So for this one, doing parts a second time, I'm going to choose u to be the 2x, and I'm going to let dv be the sine x dx. Notice I'm being consistent in the fact that I'm using that trig function for the dv part. That's real important to be consistent there. All right, the derivative of u now is down to a 2 dx. And if we find the antiderivatives here, we'll get a v over here. The antiderivative of sine is negative cosine x. Okay? So I'm going to bring this answer down here. I have x squared sine x minus. Now I'm going to need a bracket here so I can be careful with these signs. I'm now doing this using this parts formula. So u times v would be negative 2x cosine x minus the integral. V times du would be a negative 2 cosine x dx. And I'll close that off. Now I'm going to distribute this negative and do a little simplifying here. X squared sine x, that will become a plus 2x cosine x. This sign would distribute here and make a positive, but then this would come out and make it a negative 2 in front of this antiderivative of cosine x dx. Do you see that? The negative distributes here, makes a positive, distributes here, makes a positive, but then we're bringing that negative 2 constant out. Notice I am now down to a simple integrand, so I can finish finding my antiderivative. X squared sine x plus 2x cosine x, and the antiderivative of cosine is sine, so negative 2 sine x. Finally, I have found the antiderivative, and so I'll put my plus c on that final answer. Now, you can check this problem. Take the derivative of our final answer if you'd like. You might want to stop the tape and do that and just verify that we do have the correct answer here. This parts format works when you can't do a u substitution. You have a product of some functions there. It's a way of separating and being able to find an antiderivative. Sometimes you have to do parts more than once. We did parts twice in this last example. Sometimes you may have to do it 3 or 4 times before you finally get that integral part down to a simple basic formula. Let's look at another example. I have the integral of 2x cubed times e to the x dx. Remember, I'm going to choose part of this to be u and part of it to be dv. Okay? Now, here's how I would analyze this. I've got this power of x here, and I have an e to the x. This gets easier when I take derivatives because the exponent keeps going down. The e doesn't get any easier. The derivative of e is e. But I can find an antiderivative of e to the x also, can I? So I will choose 2x cubed to be my u, and for dv, I'm going to choose e to the x dx. All right, let's find our du. Du is going to be 6x squared. If I find antiderivatives here, v will be e to the x. Okay, have you learned your formula yet? U times v, 2x cubed e to the x, minus integral, v times du. You know what, I forgot my dx right there. Okay, v times du is 6x squared e to the x dx. Okay? Well, do you see that we're going to do parts again? On this, I'm going to let u equal 6x squared. dv is going to be the e to the x dx. I've accounted for everything here. du will now be 12x dx. And if I integrate here, v will be e to the x. Okay, as we did a while ago, we're going to be careful with this negative sign. I have 2x cubed e to the x minus. Now let's put a bracket. For this integral, u times v will be 6x squared e to the x minus the integral v times du is 12x e to the x dx. Now let's clean this up a little bit. I have 2x cubed e to the x, distributing the negative, minus 6x squared e to the x. This will become plus the integral of 12x e to the x dx. Now you might guess. Parts again. One more time. U equals the 12x. dv equals the e to the x dx. So du is 12 times dx. And when you integrate here, v is e to the x. Alright, so I have 2x cubed e to the x minus 6x squared e to the x plus, okay, for this one, the parts, u times v, 12x e to the x, minus the integral, v times du, 12 e to the x dx. Well, the good news is, look at this, I'm now down to a constant times e to the x, so that one I can just do from a basic formula. 2x cubed e to the x minus 6x squared e to the x plus 12x e to the x. Here I'll bring down the minus 12, antiderivative is e to the x plus c. Finally finished. Now, you may see this answer written with the e to the x factored out. Of course, you could also factor out a 2. I think I'm going to write it that way. Factor out 2 e to the x leaves x cubed here minus 3x squared here plus 6x x minus 6. Okay, so if you just distribute that back out, you'd have the same answer that you had here, but a lot of times they'll factor that out and write the answer like that. Do you get an idea? Since I started out with x cubed, I had to do parts 3 times. That's to finally get rid of all those x's. If that had been x to the 5th, I could continue this process until I eventually got down to a simple integral right here. Hopefully you won't have too many of those where you have to do parts quite so many times, but do realize that that's how we would do this problem. Alright, this one is to do the integral of x cubed log x dx. Now this one is an interesting problem. If you compare to what we just did a second ago, see this x cubed here, and we chose the x cubed part to be the u? The problem I have here is if I choose x cubed to be the u, then dv would be log x dx. Do you know how to do the antiderivative of log x dx? Have you had a formula for this? You have not. We don't know how to do that. So I cannot let log x be my dv because I don't know how to find an antiderivative of that. I do know how to take its derivative, however. And in fact, if I let u equal the natural log of x, the derivative is 1 over x dx. 1 over x is easier because I've gotten rid of that log function. So that's a good choice there. Now, that leaves for dv the x cubed times the dx. Again, make sure I've accounted for the log x, the x cubed dx in my u dv. And see, I can integrate this. The integral of dv is v. The integral of x cubed is 1/4 x to the 4th, isn't it? So I can find that. Now, let's look at our parts formula and see what happens. U times v, 1/4 x to the 4th log x, minus integral v times du. Now, I'm going to write this down and we're going to look at it. 1/4 x to the 4th times 1 over x dx. Let's simplify that thing right there before we try to find an antiderivative. Let me rewrite this first part. 1/4 x to the 4th log x. I'm going to pull the 1/4 in front. X to the 4th times 1 over x would give me x cubed in there, wouldn't it? That's just a simple power of x, so I can find the antiderivative right there. I'm going to bring down this minus 1/4. The antiderivative of x cubed is 1/4 x to the 4th. Finally finished, so I can put on my plus c. This is going to go to minus 1/16 x to the 4th when I simplify. Now, your answer is okay right here. Again, you might, however, see a 1/4 x to the 4th factored out, leaving log x minus 1/4 in here. Okay? So either of these forms is okay for the answer. Again, if you want to take time to stop this tape, you can take the derivative of this thing right here and simplify it, and you're going to get that right there. Notice we only had to do parts once, even though we had an x cubed, and the reason is that ended up over here. That cannot be dv because I don't know how to find its antiderivative. Now, we have done a number of problems here by parts, and so I put this problem in because I want to caution you, when you look at an integral, don't always assume immediately that you're going to do parts. Look at this thing. Here, if you let u be the log of x, the derivative of u is 1 over x dx. I want you to look at this. You can write this integral as the log of x to the 4th times 1 over x dx. Do you see this right here and this right here? I can do a simple u substitution on this problem. In place of log x, putting u, I have u to the 4th, and 1 over x dx can be replaced with du. It's a simple 1/5 u to the 5th plus c problem, and then you can put that back in. So don't assume immediately when you look at your problem that you're going to do parts. I usually tell my students, when you look at an integral, the first thing that you should ask yourself is, can I just do this from the basic formulas? Is it just like x to a power? Is it 1 over x, so the antiderivative is a log function? Is it a sine x or a cosine x? If it's not one of those, then I say, okay, can I do just a straight u substitution and get something like u to the n du, or 1 over u du, or e to the u du? That's my next choice. If that is not working, if the u substitution is not working, then I go to parts. It's sort of a last resort because it is more complicated, and if you try to do parts sometimes when it's not needed, you're going to get in more trouble. It's going to look ugly. I also would recommend to you right now that as you're learning to do parts, sometimes when you do an integral, you might pick a u and a dv, and you might successfully find du and v and start out. But if that integral, that second part, that v times du part, becomes more complicated than the integral you started with, chances are you've made a bad choice and you might need to go back and try it again. Let's look at another example here. The integral of e to the x sine 3x dx. Now the interesting thing about this problem is that I can find the derivative of e to the x, and I can also find the antiderivative of e to the x. I can find the derivative of sine 3x, and I can find the antiderivative of the sine of 3x. Neither one of these functions gets any easier or any more difficult, really, in terms of finding its derivative or its antiderivative. As it turns out, for this particular one, you could choose u to be either the e to the x or the sine 3x, and it really doesn't matter. The problems will be pretty much equally difficult. Now, what I'm going to choose to do is I'm going to let u be the sine 3x, and I'm going to let dv be the e to the x dx. The reason I'm doing that is because it's so easy to find the antiderivative of e to the x. That's just e to the x, okay? If I had sine 3x over here, I'd have to do some adjusting because of that 3x. But if u is sine 3x, the derivative of sine 3x is cosine 3x, and then remember you take the derivative of the argument and get a 3. I'm going to just go ahead and put that in front. So du would be 3 cosine 3x. Alright, so our parts formula says u times v. So I will have e to the x times sine 3x, u times v, minus integral. V times du would give me 3 e to the x cosine 3x dx. Okay? Now we're going to have to do parts again. Let me pull this answer down here. I've got e to the x sine 3x. This time I'm going to go ahead and pull that 3 in front and look at it like this. Okay? Now, what I have so far is the integral of e to the x sine 3x dx is equal this. Okay? Now I'm going to do parts on this. I'm going to let u be the cosine 3x. I'm going to let dv be the e to the x dx again. Okay? So du, the derivative of cosine, is negative sine 3x times the 3, so negative 3 sine 3x. V, of course, the antiderivative of e to the x is e to the x. So I'm going to pull this thing down again. E to the x sine 3x dx equals, I have this, e to the x sine 3x minus 3, I'm going to use a bracket. This integral, using parts, u times v, is e to the x cosine 3x minus the integral, v times du would be minus 3 e to the x sine 3x dx. Now you may think we're just going to keep going in circles, but I promise you there's an answer. Now let me leave that and just come right here. E to the x sine 3x. Distributing my negative 3, I have negative 3 e to the x cosine 3x. Notice the negative 3 times this negative would be a positive 3. Okay? But then this is going to come out as a negative 3. So I have a positive 3 times negative 3 is a negative 9 in front of the integral e to the x sine 3x dx. So the integral of e to the x sine 3x dx equals this minus 9. Look at this integral and look at what we started with. They are identical, aren't they? And notice we have an equation here. This integral equals this minus this minus this. We don't want to just keep doing parts. In fact, we could do parts forever and never get through, as you can see. But since these integrals look alike, think about if you have an equation that said x equals 5y minus 9x. Couldn't you add this 9x over here and get 10x? That's what we're going to do. These are like, I've got minus 9 of these integrals here. I've got one integral here. So I'm going to add 9 and bring it over here. I'm going to have 10 of these integrals of e to the x sine 3x dx equals e to the x sine 3x minus 3 e to the x cosine 3x. Then, similar to like an equation like this, if you solve for x, you divide by 10. I'm going to divide by 10. So the integral of e to the x sine 3x dx is going to be 1/10 of e to the x sine 3x minus 3 e to the x cosine 3x. And finally, I'm going to go ahead and put on that plus c because there could be a number over here whose derivative was 0, just like with any indefinite integral. This is a real interesting situation, and this occurs a lot of times when you have like a sine or a cosine and an e, because you just kind of keep going in circles. Keep in mind, I kept bringing this down where we were, did parts again, I brought that down, and then what you're looking for is hopefully this integral will repeat what you got here, and hopefully that will be something so you can bring it over and get a coefficient here and then divide by that coefficient. By the way, if you start out with your u being sine 3x, be consistent with letting your u be your trig function. If on this second time to do parts I had switched these the other way, everything would have fallen out and I would have just gotten 0 equals 0, so I would have wasted my time. So once you make a choice here, unless things are getting a lot worse, be consistent with your choices and hopefully something will repeat. You might want to look at this and follow the steps that we went through because these are really sort of interesting and pretty difficult integrals to do. That actually you can work two different ways, and I'm going to go through both of those just to show you what you can do, and then you can decide which way that you prefer. First of all, I'm going to rewrite this integral as x times the quantity 2 plus 3x to the negative 1/2 power times dx. Now, if we choose to do this with parts, I'm going to choose u to be x, and the reason for that choice right off hand is because I know that the derivative of x is just a 1 dx. What that leaves for dv is 2 plus 3x to the negative 1/2 dx. Now that is really rather complicated looking for us to come up with a v, and so what I usually recommend to my students is to use some scratch paper. We're at the point where to get v, we need to find the antiderivative of 2 plus 3x to the negative 1/2. This integral can be done with a u substitution. If you let u equal 2 plus 3x, then du is 3 times dx, and you can solve for dx. 1/3 du is equal to dx. Making the substitution, you have u to the negative 1/2, and dx is 1/3 du. I'm going to put the 1/3 in front, and you have du. and you're ready to find the antiderivative. So bring down your 1/3. If you add 1 to this exponent, you have positive 1/2, which places a 2 in front. So multiplying this, we have 2/3, and then u was 2 plus 3x to the 1/2. This will be our v. So although that was rather difficult to find, we could find it. Remember, one of your guidelines was to let dv be as complicated as it can be, and yet you are able to find an antiderivative. And certainly the du got easier. If I had let this part be u, when I take the derivative, if you think about that, you'd have to use the chain rule, and it would get really ugly. So let's run through our parts here. I'm going to come down here below this. Let me box that off so we don't get that confused with our problem. So u times v gives me 2/3 x times 2 plus 3x to the 1/2 minus the integral. V times du will be 2/3 times 2 plus 3x to the 1/2 dx. Now I'm going to rewrite this just one more time. 2/3 x times 2 plus 3x to the 1/2, and I'm going to bring this 2/3 out in front, and we have the integral of 2 plus 3x to the 1/2 dx left. Now this looks a lot like what we had right here. In fact, let me put this back up on the screen. When we did the u substitution a while ago, we were looking at this integral. The only difference is the power, isn't it? So if this were a 1/2 power instead of a negative 1/2, we would use the same u, du and everything would be exactly the same. The difference is this would be u to the positive 1/2 when we substitute instead of negative 1/2. So the difference it would make would be right here. We could bring our 1/3 down, and then when we add 1 to our u this time, since that's a positive 1/2, we would get 3/2, which would put a 2/3 in front of that. So we would have 2/9 times 2 plus 3x to the 3/2. So let's bring that solution back over here. Let me recopy this first part. Don't forget we have this minus 2/3 in front of this integral, and then when I substitute our answer that we got, 2/9 times 2 plus 3x to the 3/2 power. Then we finally have finished our integration. We can do our plus c, and then we just need to do a little multiplying here to simplify that coefficient. So we have 2/3 x times 2 plus 3x to the 1/2. This will be minus 4 over 27 times 2 plus 3x to the 3/2 plus c. Completed the problem doing the parts. I want us to look at doing this problem with just a straight u substitution, and we're going to compare our answers and see what happens. If we choose u to be 2 plus 3x, then du is 3 times dx, and I can solve for dx. 1/3 du is dx. I can replace this with u, I can replace this with 1/3 du. What I need is something to replace the x with. So you might recall we can take this formula right here and solve for x. U minus 2 would equal 3x, which means 1/3 times u minus 2 would equal x. Now let's put those in and see what happens. In place of x, we're putting 1/3 times u minus 2. And then I have u to the negative 1/2. And in place of dx, I have 1/3 du. Now the constants, 1/3 here times 1/3 here, gives me 1/9, which I can place in front of the integral. And I can distribute to multiply this out. U times u to the negative 1/2 is u to the 1/2. And then I'll have minus 2u to the negative 1/2 du. Let's find the antiderivative. We'll bring down the 1/9. U will go up to the 3/2, which places a 2/3 in front. We'll bring down the minus 2. U will go up to a positive 1/2, which puts a 2 in front. and then we have our plus c. Now we're going to multiply our coefficients and substitute back in. I have 2 over 27 in place of u, 2 plus 3x to the 3 halves. I have a minus 4 times this 1/9 would be minus 4/9 times the quantity 2 plus 3x to the positive 1/2 plus c. Now honestly, as far as doing the work, I sort of prefer this one over the parts. It's just a little bit quicker maybe for me to get the antiderivative. But I want you to notice, and you may have been thinking this already, look at our answers. Here we have 2/3 x times 2 plus 3x to the 1/2. In my second answer, I've got a minus 4/9 times 2 plus 3x to the 1/2. So that looks different, and the coefficients in front of 3 halves looks different. I want to show you that although these solutions look different, they're really the same, and I'll show you how we can do that. I'm going to work with this first answer that we got first of all. To make this easier to do some factoring, I'm going to rewrite this with a common denominator with this one. So changing this to 27, I have 18 over 27x, 2 plus 3x to the 1/2, minus 4/27 times 2 plus 3x to the 3 halves plus c. Now I can factor out 2/27, and I can factor out 2 plus 3x to the 1/2 power. So let's take a look at this. If I factor 2/27 out of this, I have a 9 and an x left. This came out. Minus, if I take 2/27 out of this, I have a 2 left. And if I factor this out to the 1/2, I have 2 plus 3x to the 1 left in there, don't I? Okay? Now, let me do one more step here. 2/27, 2 plus 3x to the 1/2. And simplifying here, notice you have 9x. This would be a minus 6x. So 9 minus 6 would be a 3x minus a 4 plus c. Okay? Now, we're going to leave that for a second. That was our first answer. We took it and factored it. Now, my second answer is 2/27 here and 4/9 here. Again, I'm going to get a common denominator. So this is 2/27, 2 plus 3x to the 3 halves. And if I get 27 here, I need to multiply by 3 over 3. I have 12/27, 2 plus 3x to the 1/2 plus c. Again, we can factor out 2/27, and we can factor out 2 plus 3x to the 1/2 power. So this came out. I will have 2 plus 3x to the first power left here, minus, if I take 2/27, I have a 6, and that came out. Look what happens when we simplify. I have 3x. 2 minus 6 is a negative 4. Now, let's look at what we have here. 2/27, 2 plus 3x to the 1/2 times 3x minus 4. Of course, I forgot to put my plus c on that one. But you see the answers are equivalent. What I wanted you to see with this example is that sometimes there's more than one way to find an antiderivative. Some people immediately see the parts and go with that. Some others might see the u substitution. The interesting thing is that the answers look a little different at first. So you may think one or both of you would have an incorrect solution. But if you do a little work on the algebra, it turns out that both answers are correct. They're just in a different form. Okay, we have the integral of arc cosine x dx. We have never had a formula to find the antiderivative of an inverse trig function. We do know how to take the derivative of an inverse trig function. I might review for you the formulas that we use. I'm going to start with the arc sine just because I remember that one. Arc sine of u, if we're taking the derivative with respect to x of that, I like to do it this way. I draw a fraction bar. In the denominator, put a square root, 1 minus u squared. So whatever this argument of my arc sine is, it's squared right here. And then the derivative of this argument goes right there. Now, the derivative of the arc cosine is very similar. The only difference is you still have this square root 1 minus u squared down here and u prime here, but you have a negative. So you may have forgotten those formulas, but we're going to need those. I'm going to do this integral by parts. Since I do know how to find the derivative of arc cosine x, I'm going to let that be u, okay? Now, if you look up here, if we're letting arc cosine x be our u, the only thing left to be dv is dx, isn't it? Well, this is easy. If you find the antiderivative on both sides, v is just going to be an x. And here, remember, we're going to put the fraction bar square root 1 minus, since the argument is x squared goes here, the derivative of x, which is a 1, goes here, and it has a minus in that formula. So, doing our parts, we have u times v is x arc cosine x minus the integral v times du. Oh, I forgot to write my dx. Let me get that on there. So when I multiply those, I get negative x over the square root of 1 minus x squared dx. Now, minus this negative, we can go ahead and change that to plus a positive, can't we? We have done parts, and we're here. Now, look at this one real close. Notice 1 minus x squared, the derivative of that is a negative 2x. I can use that x if I do a direct substitution and let u be 1 minus x squared. Du would equal negative 2x times dx. I'm going to solve for x dx. Negative 1/2 du would equal x dx. So what we can do, let me just rewrite this one time. I have x times arc cosine x plus the integral 1 minus x squared to the negative 1/2 times x dx. And we're going to do a u substitution right there. I'm going to scoot this over so I have more room. X arc cosine x plus integral. Here I've got u to the negative 1/2. In place of x dx, I can put negative 1/2 du. Now this negative 1/2 can come out in front. So x arc cosine x, I'm going to bring out that minus 1/2, and I'm going to find the antiderivative here. If I add 1, I get positive 1/2 times a 2. I'm going to go ahead and add my plus c at this point, and then I'm going to sub back in. So minus 1/2 times 2 just gives me a minus 1. My u was 1 minus x squared, and I have my antiderivative. So on this one, we did parts to get us started, and then we had a direct u substitution here to finish us off. But the nice thing is now I can find the antiderivative of an inverse trig function using parts. I wanted to do one definite integral for you. We've been doing indefinite integrals because I just wanted you concentrating on this parts formula. But we're going to combine the two at this point, and keep in mind what we do when we have numbers here, if we have a definite integral. Do you see your inverse trig function right here? You do not know how to find an antiderivative of that inverse trig function. So we're going to let u equal arc sine x squared. And then notice this time for dv, I still have an x times this dx, don't I? All right, let's get our du. Since this is an arc sine, we'll draw a fraction bar, square root 1 minus whatever this argument is, we square it. So if I square x squared, I get x to the 4th. I take the derivative of this argument, which is 2x, and that goes up there. Now, if I integrate here to get my v, the integral of x dx is 1/2 x squared, isn't it? Okay, let's start our formula. U times v would be 1/2 x squared times arc sine x squared. Now I'm going to go ahead and put that I'm needing to evaluate that from 0 to 1 because it's a definite integral. Okay, now I've done my u times v, minus the integral. Now this is still an integral from 0 to 1. V times du. Well, let's look at that. 1/2 will cancel the 2. X times x squared will give me x cubed over the square root of 1 minus x to the 4th. I apologize. On these last couple of problems, I've been so concentrating on the problem, I've forgotten to write my dx when I took du. But it is there. Okay, let's go ahead and substitute in here. If I put a 1 in, 1/2 times 1 is 1/2 arc sine 1. Notice if you put the 0 in, it will cancel out because you'll have 0 right here, so minus 0. Okay, on this next part, 0 to 1, I'm going to write 1 minus x to the 4th to the negative 1/2 times x cubed dx. I can do this with a u substitution, much like we did a little while ago. On this, I want u to be 1 minus x to the 4th. Notice then that du is negative 4 x cubed dx. I'm going to solve for the x cubed dx. Negative 1/4 du is x cubed dx. So we're going to substitute in. Now I'm going to come back and evaluate this arc sine 1 a little bit later. Right now I'm just going to bring that down. And minus the 0, of course I don't need to write that. So I've got minus integral u to the negative 1/2. This x cubed dx is negative 1/4 du. Remember, now that I'm in terms of u, these numbers need to also be in terms of u. Remember, this is with respect to x. So if x is a 0, go back here, 1 minus 0 would say u is a 1. If x is a 1, see, we're with respect to x here. If x is a 1, 1 minus 1 to the 4th is 1 minus 1 or 0. These numbers now are with respect to u. Okay, we're getting real close here. 1/2 arc sine 1. If I bring that negative 1/4 out, that's going to be a positive 1/4. I can find the antiderivative. That will go up to 1/2 with a 2 in front, evaluated from 1 to 0. Now remember, these are u values, so we can just put those straight in. I have 1/2 arc, let me write that right, arc sine 1. 1/4 times 2 would be a 1/2, so plus 1/2 times 0 to the 1/2, and then subtract 1/2 times 1 to the 1/2 power. Of course, this is going to 0 out, and 1 to the 1/2 is a 1, so this is just going to be a minus 1/2. What about this arc sine 1? Remember, if y is arc sine of 1, that's saying that the sine of y is 1. Well, y would have to be pi over 2, wouldn't it? So 1/2 times pi over 2 minus 1/2, right here is my answer. If you'd like to factor out 1/2, you could do that and write this as 1/2 times pi over 2 minus 1. Okay? So we just combined this idea of using parts, and kept in mind if you have a definite integral, you have to evaluate that. I have one more example, and we're finally going to be through with this lesson. I wanted to show you this one because this sort of involves a trick. I hate to call it a trick, but it's knowing how to rewrite this so you can accomplish the antiderivative. We do not have a formula for cosecant cubed x. Recall that the guidelines said we want u to be something so that we can find its derivative, obviously, and we hope it gets easier. Excuse me. We also said we want dv to be as complicated as possible and yet be able to find v. I'm going to write this as cosecant x times cosecant squared x dx. That's still cosecant cubed. The reason I'm choosing to do this is because I know the antiderivative of cosecant squared x. Now that's as complicated as I can get and still find v. Remember, the derivative of cotangent x is negative cosecant squared x, so the antiderivative of cosecant squared will be negative cotangent x. Now that leaves this other cosecant x over here for you. Well, the derivative of cosecant is negative cosecant x cotangent x dx. Alright, well, let's keep up with this. I have cosecant cubed x dx equals, that integral, u times v would be negative cosecant x cotangent x minus the integral v times du. Notice the negative times the negative will become positive. You'll have cosecant times cotangent squared. So cosecant x times cotangent squared x dx. Now, this really doesn't look any better, but I promise you that we are making progress here. I don't want to do parts again, but what I want to remind you is that you do have trig identities. Everybody remembers this one, sine squared x plus cosine squared x equals 1. Notice if we divide everything by sine squared x, and I'm doing this because I'm thinking you may have forgotten this identity, you get 1. Cosine squared over sine squared is cotangent squared, and 1 over sine squared is cosecant squared. So cotangent squared x equals cosecant squared x minus 1. This is the identity that I want to use. I'm going to replace the cotangent squared right here with cosecant squared x minus 1. I think you'll see in a second why I'm wanting to do that. We have the integral of cosecant cubed x dx equals minus cosecant x cotangent x minus the integral cosecant x, and in place of this cotangent squared, I'm putting cosecant squared x minus 1, that identity we just looked at. Now, hang on with me just a little bit longer and you're going to see how this thing works out. I'm just recopying this first part, and I'm going to distribute my cosecant here. I have cosecant cubed x minus cosecant x. The reason I wanted to use this identity is notice this cosecant cubed, we started with cosecant cubed, didn't we? This is going to be another one of those where we're going to be able to solve this by utilizing the idea of this equation, but I'm going to need to rewrite one more thing. Remember, if you are finding an antiderivative and you have a difference between two functions, you do this one minus this one. So let's keep in mind this sign right here. I've got minus the integral of cosecant cubed x dx, and then this minus will change that to a plus the integral of cosecant x dx. This I can add to the other side, okay? That will give me 2 of these cosecant cubed x dx integrals. And over here, I will still have this minus cosecant x cotangent x. This has gone to the other side. And the antiderivative of cosecant x, if you have not forgotten that formula, is minus the natural log absolute value cosecant x plus cotangent x. Now I'm going to go ahead and put on my plus c, and now all I need to do is divide by 2. So the integral of cosecant cubed x dx would equal 1/2 times negative cosecant x cotangent x minus the natural log of cosecant x plus cotangent x. Now usually we will close that off and just put the plus c out here by itself. Half of a constant is still a constant, so we don't worry about that too much. Now if you'd like to factor out a negative, you could change those signs to positive and your solution would look like that. So what we did here, we started off with parts and we split this thing up because we could find an antiderivative of cosecant squared. That was the most complicated thing that we could find an antiderivative of. When we got to this point, you just need to remember those trig identities and sort of think ahead. I knew that cotangent squared x could be changed into this form, and then by distributing I would get another cosecant cubed x here, which allowed me, after I split that, to move this integral over. Otherwise, we might have spent days trying to work this formula. This completes your lesson on doing integration by parts. Parts is a very important technique because we can use it when other resources fail. I just want to emphasize one more time to you, though, that when you first approach a problem, don't just jump in and do parts. Look at it carefully. Can you just do basic formulas? If not, can you do just a simple U substitution? That's easier, usually, if you can do that. Parts is a more difficult process, but sometimes it's the only process that we have that we can use to find our solution.